Okay, this is chapter 9.5. We're going to graph other trigonometric functions. So the essential question in this chapter section is, what are the characteristics of the graph of the tangent function? So guess what? We're probably going to graph tangents. What you will learn in this chapter section is how to explore characteristics of tangent and cotangent functions. Graph tangent and cotangent functions, graph secant and cosecant functions. All right, we're going to do some graphing. Okay, so we have a core concept first. Characteristics of y equals tan x and y equals cotan x. Okay, so the functions y equals tangent x and y equals cotangent x have the following characteristics. The domain of y equals tan x is all real numbers except odd multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, positive and negative. There are vertical asymptotes, so there's no value there. At these x values, the graph has vertical asymptotes, as I just said. The domain of y equals cotangent x is all real numbers except multiples of pi. So pi, 2 pi, 3 pi, 4 pi, positive and negative. And again, vertical asymptotes occur at those locations. The range of each function is all real numbers. So there are no horizontal asymptotes. It's continuous from negative infinity to positive infinity, going from down to up or up to down, if you will, the y values. So the functions do not have a maximum or a minimum, and they do not have an amplitude. So the period of each graph is pi. The x-intercepts for y equals tan x occur when x equals 0, positive or negative pi, 2 pi, 3 pi, etc. And for cotan x, it's positive or negative values of 1/2 pi's, multiples of, or negatives, I mean. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, positive or negative, and going in both directions. So keeping these in mind when graphing this makes it a lot easier. So let's take a look at example 1. Nah, just kidding. One more core concept before we get to example 1. Period and vertical asymptotes of y equals tangent bx and y equals a cotangent bx, or a tan bx and a cotan bx. In other words, there's a number in front that changes this and number in front that changes that. The period and vertical asymptotes of the graphs of y equals a times tan bx and y equals a cotan bx, where a and b are non-zero real numbers, are as follows. The period of the graph of each function would be pi over the absolute value of b, and the vertical asymptotes for y equals a tan bx are odd multiples of pi over 2 times the absolute value of b. The vertical asymptotes for y equals a times cotan bx are at multiples of pi over absolute value of b. Okay, so when we put a number in front of the function or in front of what we're taking the tangent of, these characteristics will come into play, and we'll take a look at that in examples. All right, so here's example 1, graphing a tangent function. It says to graph one period, g of x equals 2 tan 3x. Describe the graph of g as a transformation of the graph of f of x equals tan x. So I brought in the rules from the previous core concept, and the period of the graph of each function is pi over b, absolute value of b. Okay, so the first thing I'm going to do is I'm going to say identify my a and my b. So a is right here, a is 2. B is right here, and that is 3. So now I'm going to find out what the period is. I want to know what the period of the function is, and the period of it is pi over the absolute value of 3, which is b. And obviously the absolute value of a positive is just itself, so the period is pi over 3. All right, vertical asymptotes is the next thing you want to find. So the vertical asymptotes are, so I'm going to say VA for short, vertical asymptotes are pi over 2 absolute value of b, which is pi over 2 times 3, which is 6. So the vertical asymptotes occur at pi over 6, plus or minus, obviously. And so I'm going to graph those. So I already have vertical lines here. So if I put, I want to be really accurate here. So I'm going to use a circle from center, like so. think it was just off a hair to the right there. So I want to create a grid. Right here is one, and right here is the other. I'm just using a unit circle, or a circle, just to get these the same distance apart. And I'm going to move my vertical asymptotes to those locations. So obviously you draw these with a ruler on paper. And what are those locations? Well, it's pi over 6 over here. And this is, let's make this bigger. Let's make that our halfway point. So bear with me. So I'm going to do a unit circle, or a circle again, not necessarily a unit. Okay, so there was one. So then if I want to move that center to here, I'm just using this circle to get equidistances for my values. So there's one. And then if I move this to right there, then I find this right here. And so there, you could use a ruler, of course. So let's make that our pi over 6 distance. Okay, so pi over 6 would be right here. And this distance over here is negative pi over 6. So pi over 6 to here is a distance of pi over 6. From here to here is a distance of pi over 6. So that's 2 pi over 6, or pi over 3. And there is our period from asymptote to asymptote. So we then want the midpoint. Well, half of pi over 6 is pi over 12. And this would be negative pi over 12. Okay, so that's the first step. Find the period, find the asymptotes, and do a midpoint from the center origin over. Okay, so now speaking of the origin, what is g of 0? So g of 0, in other words, if I plug in the origin, x is 0, what is y? So it's going to be 2 times the tangent of 3 times 0, right? Well, 3 times 0 is 0. The tangent of 0, well, if you don't remember, now I'm going to go to a unit circle just to be really quick here. Let's make it thinner, and let's make it red. It's only going to be temporary. I just want to explain to you on this grid. If this were a unit circle, ignore everything else. This point right here is over 1 up 0. And that would be the tangent of 0 right there. This is a graph. This is an angle of 0 degrees where our initial and terminal side are coincide and are sitting right there at 1, 0. Tangent is sine over cosine, which is 0 over 1. So tan of 0 is 0 over 1, which is 0. So we get the point when we plug in x is 0, we get y equals 0. So that's the origin. Okay. So, and now I just want to get rid of all this. Okay, so I just wanted to explain to you how we get those values from the unit circle real quickly. All right, so we have a point right here. And we have a vertical asymptote, so this thing's approaching there. So I want to know what pi over 12 is. Okay, so I'm going to use my calculator. And I'm going to turn it on. And I'm going to go to mode. Now we're working in pi units, so that is radians. So leave it in radians and clear the screen and plug in your function, which was 2 tan 3, and I want pi over 12. So I do secant pi divide 12, close the parentheses and hit enter. And the value at pi over 12 is 2. Okay, so now I'm going to, let's make this, well, let's make it black for starters. Let's make this distance 1, and this distance 2, and this distance -1, -2. Okay, so at pi over 12, the function's value was 2, which is right here. Now I want to do negative pi over 12. So I'm just going to hit second entry. And I'm going to come in here and insert a negative sign and hit enter. And I get -2. So 2 times the tangent of 3 pi over -12, or negative pi over 12. I could have put the negative over here too. It's -2. So we are down here. So now we can see that this function is coming up like this, turning, going through the origin, going up like this and coming closer and closer and closer to that asymptote and going to infinity and negative infinity in between there. So there is the graph of 2 tan 3x from negative pi over 6 to pi over 6. So then it says, compare it to the graph of f of x equals tan x. Well, it's a vertical stretch by a factor of 2 and a horizontal shrink by a factor of the inverse of this. So vertical stretch by factor of 2 and a horizontal shrink by factor of 1/3. Okay, vertical stretch by a factor of 2, horizontal shrink by a factor of 1/3. And that's how you graph a tangent function. Now try this with example 6 in your exercises, or problem 6 in your exercises. Okay, so here's example 2, graphing a cotangent function. So as it says here, to graph one period of g of x, which is cotangent of 1/2 x, and describe the graph of g as a transformation of its parent. Okay, so the first thing I'm going to do is, like before, what is a? Well, in this case, a is in front of cotangent, there's nothing there, so it's 1. And b is in front of the x, so it's 1/2. So a is 1, b is 1/2. So I want to know where the x-intercepts are. We're doing cotangent, so it's multiples of odd pi's over 2. Okay, so in this case, the period is, let's write period. Period is pi over absolute value of b. Okay, the period of the graph of each function is that pi over absolute value of b. That would be pi over the absolute value of 1/2, which is 1/2. And pi divided by 1/2 is pi times 2, or 2 pi. So our period is 2 pi. Okay, so we want intercepts now. So intercepts. And I'm not going to use my calculator this time, because if we use a calculator, think about that. All you have to do is go to y equals and graph it and look at it. So we're assuming you can't use a calculator. We want to be able to do this without a calculator. How do I find the x-intercepts of cotangent? Well, it's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Okay, that's the parent function. Now this thing is vertically or horizontally shrunk by a factor of 2, or stretched, I mean, horizontal stretch by a factor of 2. Okay, 2 is more than 1. It's not a shrink, it's a stretch. All right, so period's 2 pi. So what I'm going to do is come out here and call this 2 pi. Halfway, let's call that pi. Halfway, pi over 2. Halfway between pi and 2 pi, 3 pi over 2. Okay, so there is our graph. And what is cotangent of 0? Well, cotangent is cosine over sine. So cotangent of 0, without getting the unit circle out again, is 1 over 0, or undefined. So that tells me right there that I have a vertical asymptote right here on the x-axis. So I'll just set that off to the edge a little bit. And this is obviously 0. So let me just label this my y-axis and this my x. So I have an asymptote there. And the period's 2 pi. So the other asymptote is at the other end of the period, which is 2 pi. So I'm graphing in between 0 and 2 pi. Okay, so that's that. So x-intercepts are going to be, oops, I don't have my pen. Why is it black? X-intercepts are going to be pi over 2 pi over 2, x-intercepts are pi over 2 times b. And our b is a half, and it's going to be comma 0. So pi over 2 times a half is just pi, right? 2 times a half is 1, so we're going to get pi comma 0. So over to pi 0, there is my x-intercept, and that's it, because if I go to the next one, we're going to be beyond 2 pi. All right, so there's our vertical asymptotes and our center at pi, our x-intercept. And then what we want to do is, I've already done the asymptotes, and the halfway points now would be pi over 2 and 3 pi over 2. All right, so halfways is how the book shows this. So they're going to do halfways, and it's not going to be pi over 2b. It's going to be halfway from 2 pi over 4 times b, comma 0. Or not comma 0, comma a, whatever that value is, which is 1. Okay. Okay, so what's that going to give us? That's going to give us pi over 4 times b, which is a half, comma 1. And simplifying that, we get pi over 2, comma 1. So go over to pi over 2, and let's just say 1 was right here, and 2 is up here. I am right there. Pi over 2, comma 1. The next point is going to be 3 pi over 4b, because we're doing the odds, right? 3 pi over. So this one is going to be 3 pi over 4b, comma a, which becomes 3 pi over 4 times a half, comma a, and it's the negative of a for the other next one. Okay, and so I should have a negative here, because it's coming down like so. And that's going to give us 3 pi over 2, comma, negative 1. So I go over to 3 pi over 2, negative 1's here, negative 2's here. 3 pi over 2, negative 1 is right there. And it's going to go up to infinity here, come down, whoops. It's going to come down through this point here, through this point here, curve, keep going, and go like that. So that is the graph of cotangent of 1/2 x, which is a horizontal stretch of 2. Okay, so it's a horizontal stretch of a factor of 2. And there's no vertical stretch because a was 1. All right, so that's graphing the cotangent function. Now try exercise 8. Okay, another core concept, characteristics of secant and cosecant. So the function y equals secant x and y equals cosecant x have the following characteristics. The domain of secant is all real numbers except odd multiples of pi over 2. There's a vertical asymptote there. The domain of cosecant is all real numbers except multiples of pi. At these values, the graph has vertical asymptotes. The range of each function is y is less than or equal to -1 and y is greater than or equal to 1. So the graphs do not have an amplitude. The period of each graph is 2 pi. Okay, so we're going to take a look at that in examples. Okay, so graphing secant is a little different since it is the inverse of cosine. We're going to graph cosine. So I'm going to graph, step 1 is graph y equals 2 cos x. So when you ever see secant and a is 2, b is 1. So I'm going to say that a equals 2, b equals 1. So since I have 2 secant x, I'm going to graph 2 cosine x. Well, to graph 2 cosine x, what's the period of a cosine? Well, the period of a cosine is 2 pi over 1, 2 pi over a, or 2 pi. So the period of cosine is 2 pi. And remember where cosine is. So if this is 1 1, 2, 3, 4, like so. Cosine of 0 is 1, but we're stretching it up to 2. So cosine of 0 in this case is 2. If I go out to, let's say, pi, and then 2 pi, the cosine of 2 pi is also 2. And then if I go to -1, -2, the cosine of pi is -2. So graphing cosine is going to come down like so, turn, come back up, and do that. So there is the cosine of 2 pi. I'm also going to continue it. Let's see. Let's go on the other side as well. So this continues. And this is pi. This is pi over 2. This is 3 pi over 2. And so negative pi over 2 is going to bring this back down. Let me erase this. It's too curvy there. It flattens out too much. So it's going to come up like so. Curve, turn, come back down, and continue in that fashion like that. So it's here, it's here. It's 0 at pi over 2. It's -2 at pi, and it's 0 at 3 pi over 2. Okay, all coming from the unit circle, by the way. So there is the cosine of 2 pi. All right, so now that I've graphed the cosine of 2 pi, remember what it said in our core concept. Where are their vertical asymptotes? The domain of secant x is all real numbers except odd multiples of pi over 2. So at pi over 2, we are going to have an asymptote. Let me just copy it from previous page. Let me just copy this so I don't have to draw a new one. Okay, so there's going to be an asymptote at odd multiples of pi over 2. 3 pi over 2, -pi over 2. Okay, so there's our asymptotes right there. Okay, and so now the graph is going to be, remember, it's an inverse, so it's reflected in y equals, it's going to be reflected over. So it says to graph asymptotes of G, which we've just done. Then you plot points on G such as 0, 2, which is here, and pi, -2, which is here. So now we're talking about our function we're dealing with, which is G. So let me highlight that. We are doing G of X right now. So I'm going to graph that one in green. So 2 secant of 0 is going to be here, and 2 secant of pi is going to be right there. But what it's going to do is it's going to turn and go the other way, and it's going to mirror with the function we have here. And that's why it said there is no maximums or minimums. So it's like so. So the green, let me turn that a little bit there. Let's clean this up a hair. Oops. Oops. Okay, so there is the graph of G in green. So it is a vertical stretch by a factor of 2. Okay, so it says to describe the graph G as a transformation of the parent function secant x. So secant x would have been up here at -1 and 1, and this thing is stretched vertically. This doesn't look like the same distance here. This looks wider, but they are the same. I just didn't draw it out properly. Okay, so the green is 2 secant x. Now try exercise 20. Okay, example 4 is graphing cosecant. So graph one period of g of x equals 1/2 cosecant pi over, or pi x. Describe the graph of g as a transformation of the parent cosecant function. All right, so again, A equals a half, B equals pi. And the first thing we want to do is find the period. So the period is going to be 2 pi over B, which is pi. And that comes out to be 2. The period is 2. So now in this case, our x-axis is not going to be pi values. It's going to be numeric values. So if this is 1, this is 2. And well, actually, let's spread it out because we're only going to graph the, let's put 2, oh, I don't know. Let's see, how about out here and make this 1. Here's 1, here's 2. Same distance this way, same distance this way, approximately -2, -1. And then up here, let's put 1, and down here, put -1. So the period is 2. Now remember, we're graphing, first we're going to graph the inverse, the parent, which is, and cosecant, the inverse is sine. So I want to graph y equals 1/2 sine of pi x. So the period is 2 pi. I'm sorry, the period is 2 pi over pi, which is 2. So remember, sine starts at the origin and it goes up. At a half, it's going to be 1. And at 1, it's going to be 0. And at 3 halves, it's going to be -1, and then back up to 2. Remember what sine looks like. It curves up, comes down, and turns and goes back up. And there is one period of the parent function pi. But then this one is vertical shrink by a half and a horizontal stretch of pi. Okay, so let me just fix this a little. It's not very. So I want that to come up like so, nice and smooth. There, that's better. So this is 1 period of pi. And it's going to continue, of course. So it's going to come down to -1 at a -1/2, back up to 0 at -1, back up here. So it's going to, on the other side, do this. Okay. So there is the sine function. All right. So then we want to go back and look at, I didn't copy it, but anyway. So cosecant right here, the domain is all real numbers except multiples of pi. At these values, there's a vertical asymptote. Okay, so in this case, pi over pi is 1. So there's going to be a vertical asymptote at 1. Remember, our b is 1. So we're going to have vertical asymptotes at 1 in this case. So let me copy this over. Okay, so at 1 and at 2 and at -1. Or at -1 and 0, actually. Okay, move this up a little. Okay, so there are our asymptotes. So they occurred at 0, 1, and 2, and -1, of course. So multiples of 1. So there they are. And now we're going to graph our inverse function. I'll do it in green again. So it's going to be here, and here, and here, and going the opposite direction. Okay, get the idea? And so in the green is our 1/2 cosecant pi x. And so that is a vertical shrink by a half. Vertical shrink by 1/2 and a horizontal Okay, so it's pi, so it's going to be a shrink by the inverse, or the reciprocal of pi, 1 over pi. Okay, vertical shrink by half, horizontal shrink by 1 over pi of the graph of f. So that is how you graph cosecant. Now try that on exercise 18. Okay, so that brings us to the end of chapter 9.5. I only gave 4 examples or exercises, one for each example, 6, 8, 18, 20. I would recommend doing more than that, but I'm just going to have you try one of each for the homework assignment. And then 29 through 34 is matching. Check with your calculator until you get a hang of this and make sure you're doing it correctly. Okay, thanks for watching and have a great day.